Okay, guys, take note. Today I actually wanted another lesson for essay base. Okay, right. But it's too much. Okay, they say cannot no time. Okay, today right, we're gonna cover the whole content. Okay, it's quite demanding. Right. Okay, let me just very quickly recap what we did in the last lesson first. Okay, past couple of lessons. Okay, first lesson, right? Okay, come on, okay. The first lesson, the most important thing we went through is all the formulas. We got Ka, Kb, Kw, all the pH, pOH formulas, so on and so forth. Basically, the first lesson we didn't cover much. Okay, what's important in the first lesson, right, was the dissociation calculations. Okay, so the question type, right, if you forget how to calculate, it's fine. Later we'll go through. Okay, the second lesson was where all the serious shit begins. We talked about salt hydrolysis, right? Okay, everything that we discussed last lesson. And we also discussed buffers. Wow. Now, the buffers, right, we actually haven't finished yet. Okay, there's like a few stuff there, okay, but it's filled up. It's if you are building up last week's lesson, okay, not much. Okay, I'll just recap buffers because today we're reading. Okay, for today's lesson, right, we're gonna finish up buffers, but what's the most important here is titration curves. Some of you guys have seen this already, and then you just go, what the hell, right? I can tell you first, a titration curve is a simulation of buffer, salt hydrolysis, and dissociation. Meaning they can give you one fat graph, right? And then they can split it into like 5 parts, and then they can ask you multiple questions regarding all these 3 question types. Again, today we're just going to do a lot of calculations. Okay, so please pay attention. Okay, today we have to go over like the 20 pages, right? Okay, so we'll go over to page 37 first. Okay, today I will recap a bit of what we did last week for buffer, and then we'll continue on buffer. Now, first question to ask you guys: what is inside a buffer? Okay, I don't have to look at definition. Okay, we have to have how many species in a buffer? Two. What are the species in a buffer? Conjugate. Okay. In other words, it must contain a conjugate acid-base pair. Right, guys, what is a conjugate acid-base pair? What's their relationship? What do they differ by? One H plus only. Please take note. Okay, you must know how to identify this. Differ only by one H plus, nothing else. Okay, but can a buffer contain any strong species? No. Okay, it must only contain weak species. So no strong species allowed. So you cannot tell me, right, that you have HCl. You cannot tell me you have NaOH. None of those strong stuff that you learned in secondary school. Very easy to tell one. Like you see one strong items, right? You just say, oh, okay, no buffer created. Okay, that's what we did for the basics. Okay, guys, how does a buffer operate? When you throw in, okay, let's just say I have a conjugate acid-base pair, okay, correct? NH3 and NH4 plus, correct? Okay, that's a buffer. Now, when I throw in H plus, whose job is it to remove the H plus? Okay, if I throw in OH minus, whose job is it now? Okay, what's this reaction called? How do we remove it? Okay, neutralization. Okay, so buffer, right, operates via neutralization. Guys, can I remember if there's a neutralization reaction, should I use a full arrow or reversible? Okay, full arrow. Okay, remember I told you guys about the arrow rules. If it's neutralization, you use a full arrow. If it's not neutralization, what do you use? The reversible arrow. Yes, exactly. It's only one or the other, guys. It's very binary. Can see that? Canvas? Okay, arrows cannot get wrong. Meaning to say, guys, whenever we're doing a buffer question, can you use a reversible arrow? No, I do not want to see any reversible. Please take your points very carefully. Okay, so it uses neutralization equations. I have to write out this already in the notes. Okay, went through other stuff as well, right? Some calculations here and there which we'll go on today. Okay, but can you turn over to page 37? Okay, today we're going to look at this thing called maximum buffer capacity. It sounds very, very cheap and whatnot. Okay, but let me just give you guys an example. All right. Now, first of all, you look at this buffer over here, guys. Imagine, now I talk about proportions. I have 80% NH3 in the buffer and only 20% NH4 plus. It is just a random proportion. Guys, can you look at this proportion here and tell me, right, is it better at removing H plus or better at removing OH minus? Okay, why? Okay, good. You have more base, so it's better at removing H plus. Okay, go and write this down. I'm going to draw this out. Okay, I will get to my point later. This buffer is better and removing H plus. Okay, I'm pretty sure you all know why already. You have more base. Okay, conversely, I can always switch the conversation around. I can have 20% NH3 and 80% NH4 plus. And I'm pretty sure you all know what the answer it is already. It's the buffer, what's the buffer pattern removing? Okay, OH minus. Okay, just draw this in because sometimes you all might forget what is this segment trying to ask for. Okay, what I'm saying over here, right, is this proportions is called buffer capacity. Okay, so look at the first line. Buffer capacity, to put it very simply, is the proportion of each inside the buffer. Okay, I know the notes is something a little bit different. Similar ideas lah. Guys, can I ask you all, right, what do you think is the best proportion? 50-50. Because guys, a buffer aims to remove both H plus and OH minus, right? So you should be equally good at removing both of them. That means the best case scenario is where your acid and conjugate base is both in equal proportions. And guys, what is this called? When your acid and conjugate base is equal in proportions. No, race mate is for still enantiomers. Okay. We look at this as maximum buffer capacity. Oh, guys, the word maximum simply is like the best buffer. Okay, the best version of the buffer. Okay, you can see that. Okay, currently 80-20 is a buffer. 20-80 is also a buffer. But I'm talking about the best version of the buffer, which is 50-50. Because the logic is you want to equally get rid of H plus and OH minus equally well, right? You can see that. Okay, and there's this thing, right? MBC for short, MBC, right? Okay, it's a very, very common concept later in titration curves. What I need you all to know now, okay, I know there's a few formulas at the bottom of the page. I'm going to show you guys how the formula of MBC is calculated. Okay, guys, how do you calculate the age of a buffer that has maximum capacity? Okay, take a look. Remember the formulas from last week. Look at the board, don't look at the notes yet. pH equals to pKa plus log. Guys, what's at the bottom? If I use pKa, what's at the bottom? Acid. Okay, very simple. If acid is at the bottom, who's at the top? Okay, in the top, okay, correct. Or conjugate is okay, guys, in this case, acid and conjugate is what's the ratio here? Okay, so you go and type log 1 into the calculator, what will you get? 0. 0. In other words, for maximum buffer capacity, this portion is how? Can you all see, right? The formula is just pH equals to pKa. Okay, what is this trying to do? If the question asks you guys, find the pH in which the proportions are equal, it's just equal to the pKa value. That's it. You don't even need to do the ratio because log 1 is equal to 0. You see that? Similarly, if you take out the pKa version, right, you'll get POH equals to pKa because the ratio will be cancelled out either way. Both ways work. Okay. Depending on what the question is given you, K or KB, you're going to use the appropriate one. You go and highlight this formula. It's only for if it's yeah, correct. Only if it's equal. Okay, I know the notes ask you guys to write it down, so let me just write it down for you guys. So, okay, write this first part down, and then just annotate yourself because log 1 is equal to 0. And you repeat the same thing for POH. Guys, can you tell me the POH version? POH equals to pKa plus. Okay, good. The bottom is always base. Okay, focus on the bottom first. This is the best way. Remember this method. Okay, so what's on top here will be your conjugate S. Okay, so far. Guys, again, the ratio for maximum buffer must be the same. So log 1 is equal to 0 once again, and then you have your formula pH equals to pKa. Okay, guys, is this portion here difficult? No, that's pretty much it. That's pretty much it. So let me repeat it. Last lesson, I just told you guys a buffer must contain a pair. But today we're going to look at the proportions of each. The best proportion is the same. Okay? Once done with this, turn over to the next page. Okay. I'll erase this part. I think you're all done with this. Hey, you want to read? Okay. Hey, my brother, when you have one big box over there, you got a second. Oh, take it out of the box. Okay. Hey guys, we finish our buffer very quickly. I really need to move on already. Okay, so look at page 38. Okay, now effective buffer range. Now guys, it's a buffer, a magical solution where you put H plus, like a lot of H plus and the pH will change. No, guys, buffer you all must acknowledge, right? Eventually, it will change, yes, small amounts. Only small amounts, then the pH will stay relatively constant. But after you add until a certain point, what is this threshold, this boundary at which the pH will start changing? Okay, so this is what I'm going to be discussing right now. There's this concept over here called effective buffer range. Okay, guys, I need you all to look at it in a more simple manner. Effective buffer range just means the pH range at which the buffer works. Okay, so let's write it down. It is the pH range at which the buffer actually works. So guys, beyond this pH range, the buffer is no longer a buffer. It's just a normal air solution. Make sense so far? Okay, let me just go straight to the formula first. What is the formula to calculate the buffer range? Now, I know in the notes they derive all that shit, right? Okay, so I just go very briefly up. Can you come back to this formula over here? Okay, guys, the ratio of acid to conjugate base should maximum be 10:1. Okay, so let me just say, the buffer only works if the maximum is 10:1 ratio. To put it into numbers like what I saw just now, guys, is 80-20 okay? It is fine, right? This is not 10:1, right? This is like 4:1, still okay. Still quite healthy. But guys, you cannot have too much of one thing and too little of the other. Does that make sense? Okay, you must have kind of like a healthy balance, you know. Okay, you can't have such a skewed number. Meaning to say, guys, is this okay? Is 95.5 okay? No, okay, horrid. Okay, this is not a buffer. So guys, we're going to write down these examples. They're not in the notes. Okay, the notes, they have the formal definition, which is a bit hard to understand. Okay, so we're going to write this down. 80-20, healthy balance, right? Okay, you need a balance. But 95.5 is terrible. Okay, guys, what's the boundary here? 10:1 is what percentage? Okay, the max that you can have is 91:91. Okay, to be mathematically accurate, right? Yeah, lah, it's 91:91. See that? Okay. So a buffer, right? You cannot have 99:1. Okay, that one's not a healthy balance. That one, the buffer isn't a buffer. And guys, okay, you go the other way, right? You can also have 10:1 the other way around. Can you see that? This is how the formula here is derived. Okay, guys, you place this formula into this ratio, and I can show you all that after all the math is done, the effective buffer rate, okay, go and highlight this formula, is pKa plus minus 1. Very simple ratio. Let me give you some examples. Please write these examples down. Okay, so for example, the pKa of ethanoic acid is 4.74. Can someone tell me a buffer containing ethanoic acid and its conjugate base, what is the range of pH where it's a buffer? 3.4. Okay, exactly. So the effective pH range of a buffer is 3.74 to 5.74. Can you see it's plus minus 1? Okay, guys, that means if the pH of the buffer suddenly is 6, is that a buffer? No, it's just a normal mixture. Can you see that? Okay, when the pH of the solution is 7, that shit cannot resist pH change, right? It will just do normally. Okay, but within 3.74 to 5.74 pH, it will be very, very stable. The pH will be maintained very stable. Does that make sense? Yeah. Okay. Okay, how do you determine this? Again, you need the pK of the species. Okay, good. We have another example. Okay, let me give you another example here. The pKb, right there. Okay, we look at NH3. The pKb of NH3 is also 4.74. Can someone tell me what's the effective pH rate of this buffer? Okay. Hey, come. Tell me this. NH3, the pKb is 4.74. Okay, so you do the plus minus 1, right? It's 3.74 to 5.74. But guys, is this pH of everything? Yes, okay, go ahead, highlight the notes. If they give you pKb, please take note. It's 40. But they want effective pH rate, so that's what I do here. Okay, 14 minus that value. Go and calculate. I don't know what it is. Oh, okay. 8.26 to 10.26. Guys, okay, please be very careful here. This one is not the correct answer. You must convert it. Does that make sense? Yeah, okay, look at the data they've given you in the chapter. Use these two examples. I hope you understand this. I guess. So if it's KB, you have to do the minus. Yes, correct. Okay, guys, so for example, if the pH of this solution is 7, okay, look, if the pH of this solution is 7, is that a buffer? No, it sucks. Okay, it must be within this pH, right? Very strict. Then the buffer can actually work like a buffer. Can see that? Okay, yeah. Okay, with that said, right? Okay, I want you to take a look at page 39. There's this question once again, right? Two things they want you to do in this question. Okay, so we're going to take a look first. Okay, look at this question. Okay, they are saying that you need to choose one of these acids. One of these acids can create a buffer at pH 4.25. Okay, so the pH of the buffer that I desire right now is 4.25. Which one of these acids can create a buffer solution? Okay, so HCl2HY. Okay, good. So at the right hand side column, I want you to get it right now. For HCl2H, the effective buffer range is from where to where? Okay, 2.74 to 4.74. Is there any other answer actually? Okay, good. HNO2, what's the range? Okay, 2.34 to 4.34. Okay, good. But there's only one option, the best option. So between these two guys, which one do you think is better? First one. Why? The range. No, the range is not bigger. More private to that. Ah, okay, I get what you're trying to say. So you take a look, the answer is the first one. I want you to visualize how. Guys, what is the best version of a buffer? What is it called? 50-50 maximum buffer capacity, correct? What's the formula again? You want the pH to... I mean, what? No, pKa. Guys, listen up. You want the pH to be as close to the pKa as possible. Okay, so we're write this down. You want the pH to be as close to the pKa as possible. Because if it's super close, then you will achieve the best version of the buffer. Now you take a look at a diagram we draw here. If this is 2.74 and then this is 4.74, where is 4.25 located at? Somewhere-ish over here, right? It's not in the middle, close. Okay, but look at the other one. If you have 4.34 at the end, where is 4.25? Right. Very, very far to the right, correct? Okay. Now, which one is better? Now, remember, you want the pH to be equal to the pKa. In this case, what's the pKa of each one of these salts? It has to be in the middle, right? The middle is the best. Can you see that? Okay, the middle pKa, this one is 3.74. This one you can find the notes at 3.34. You want to be as close to the pKa as possible. Can you see that? Which is in the middle of the effective pH range. Can you see that? The range is plus minus 1. But you want it to be as close to the middle because it's closest to the pKa. Can you see that? So in other words, you compare these two guys here, you want to be as close to the purple line as possible. That's why the first one is better. Okay, you don't have to explain this, I just need you to understand. Okay, draw the diagram out. Can? Hey guys, after they ask you to calculate already, after they ask you to choose this guy, I need you all to calculate the ratio of the conjugate base and the acid. How do we do that? Hey guys, how do we do this? Okay, we need to use which formula and read it out. You have to calculate the ratios of the two species. pH equals to pH plus log. Okay, that's the acid conjugate base. Okay, conjugate base on top, what is it called? Is it the okay, CO2 minus plus. And the bottom is just your acid. Guys, the question is asking us, right, calculate this ratio here. So we're plugging the values. What? Oh, it's going to take one more. Okay, you got to calculate now. Go. Okay, so are you going to yeah, then ask. Yeah. No, then you no, go where? Equilibria. Oh, nobody asked you. Asked you. Go to this one. Okay, no one can read the one. Here, up there. Lord. Wait. What is that? Hey, no, go. There is question. Yeah. Okay, excellent. Was it? I know. Okay, the rest. What the fuck you cook? Yeah. Log is very no. Log. I know that. It's a different question, right? In the I got the log that thing. Go to some number. I have to put 10 to the power of negative. No, the negative not here because this is log. Oh, okay, no. Okay, no. Okay, look. Okay, so the pH here is 4.5. pKa is 3.74. It's just math log, right? Okay, the logarithms, I'm not here to teach you all log. Okay, so the ratio here should be 3.24. This shit here. Look at it. Okay, let's move on. Is this a healthy ratio? The best, what's the best ideal answer? You want the answer here to be what? The best. One, correct. Equal ratio. Okay, but sometimes that's not possible. Okay, well, this is within the range, right? What's the maximum? 10. Correct. Or 1 is more over 10. It's acceptable. Yes. No, his logarithm kind of screwed up. Guys, once I'm done, okay, we need to move on to okay, here turn over to page 14. Okay, we're gonna look at application. So we learn buffer for plug, right? Okay, buffer in real life, what is it used for? Is your goddamn body. Okay, your blood, okay, blood actually has buffer system. Okay, how does this work? Okay, you all look at the box, right? What did they ask? Yeah, I don't know what the question is. What did they ask? How does the blood buffer regulate? Yes, okay. How does the blood buffer regulate pH? Okay, guys, this happens right during vigorous exercise. Okay, there is a purpose over here. Okay, let me give you some contextual information first. Okay, look at the two equations they've given you guys. Okay, you do not have to memorize these equations, thank God. Okay, because these equations that they will just give you the exam. Yeah, okay, they will give you this equation and they ask you guys to explain. Alright, so you see there's reversible errors here. Which, yes, I understand that this isn't exactly neutralized. Okay, but we're going to use the Arrhenius principle to discuss how this system works. Again, it will make sense. Okay, so let me label this as equation 1, equation 2. Now, before I go into the thing, I need you to know that your blood contains two species, Okay, HCO3 minus and okay, the blood contains C2P6. Now take a look. You cannot tell me CO3 2 minus. A lot of people somehow tell me blood contains this. No, okay, they test it as before. It is freaking easy. You just need to tell me what's example. But a lot of people just forget to study, then you don't give me CO3 2 minus. Wrong. Go and write this down. No go. Okay, your blood only contains these two species. No, it's not in blood at all. Yes. Okay.
How did you come up with this shit? Because you have not exist, bro.
Ask a phone. Right, okay, so take a look. They are differing by 1H plus. Can you see that? Okay, how does this work then? You look at the equations on the right. Now, what happens during vigorous exercise? Sometimes you all feel your muscles a bit sore, right? Okay, it's because of this thing called lactic acid. Yes. Okay, so vigorous exercise produces lactic acid. Just dying. How do you just die in class? Please stop beating each other. Stop touching each other. Okay, stop touching each other. Stop getting hard in class. Okay, take note, the pH of your blood must know this. Your blood must be 7.4 pH. Don't ask me why, it's just like that. Okay, the blood, if it's too acidic or too alkaline, you will die also. Okay, so when I write this down, you must know the pH of the blood must be consistent at 7.4. Okay, they will sometimes tell you, but just know that it's not that hard to memorize. Okay, meaning to say, if you exercise, guys, technically, if your blood doesn't have a buffer, you exercise, your blood becomes more acidic, right? And then you just die, right? Okay, but that's not what's supposed to happen. Okay, we are going to maintain 7.4 using a blood buffer. So guys, let's begin our explanation. Okay, when you produce lactic acid during exercise, what happens? H plus increase. What will this cause? You shift towards the left. Okay, then that means you have more of. Okay, now you notice that this also appears in the first equilibrium. So if there's more H2CO3, what happens now? More H2. You dissociate to produce more CO2, right? Okay, so what happens when more CO2 in the body? Does the body like carbon dioxide? No, you want to exhale the shit, right? So if there's a lot of carbon dioxide in your body, how will your body respond to maintain the equilibrium? Your rate of breathing. Yawn. Bro, just say you yawn. No. Okay. Faster. Does that make sense? If you have too much carbon dioxide and you don't breathe fast enough, your blood pH is going to drop and then you're going to die. So the body responds by breathing that shit, to expel that shit. Okay, that's how you breathe faster while you exercise. Okay, so come, let's take a look. The first point is just telling me now, okay, during exercise, concentration of H plus increases. Okay, don't tell me about lactic acid. Okay, concentration of H plus in the blood increases, causing the position of equilibrium of equation 2 to shift left. Okay, very simple stuff. Okay, then you will produce more H2CO3. So thus, concentration of H2CO3 increases, causing POE of equation 1. So you need to always specify which equation. To also shift left. Which this case produces more carbon dioxide. Okay, when you produce more carbon dioxide, what do you do next? Okay, you exhale faster. Okay, so you tell me along those lines. All right, okay, rate of breathing. Exercise you are born spell excess You have a collective of one brain cell as four of you have collective of one brain. Okay? Okay, but you can't just tell me expel excess carbon dioxide because now we need to relate it back to the problem. Okay, when you expel the excess carbon dioxide, CO2 will drop, right? Okay, when CO2 drops, your station CO2 also drops, and then it will just drop back to the equilibrium. You see that? Drop back to a healthy ratio. So you just need to mention that also. Okay? Expel excess CO2 until the ratio of the two acid-base conjugate pairs, H2CO3 to HCO3 minus, is restored back to equilibrium. You again don't need to tell me until so detailed. It's something increase back. It just say restore to equilibrium. Okay, highlight this keyword because I feel that a lot of people stop at the expelling of excess carbon dioxide. And no, that's not it. You need to relate it back to here, this context. Okay, so what if you expel excess carbon dioxide? To reduce it back to your equilibrium. Okay, tell me about rate of breathing. Okay, the first two, right, really not much. Maybe just know that you produce acid of blood. Okay, common question, and guys, you can get 2 marks out of this because it's not hard, right? Okay, we're finally done with buffers. Okay, we don't have much time for titration, so we need to make it faster. Okay, can? Or you're like the guy that playing land, right? They start clapping. Okay, can?
Bro, you also have a funny laugh. You know this is
Yeah, no, louder.
This is a what was the secondary laugh, right? You don't know this.
Okay, maybe. Alright, okay guys, can you take a look at page 41? Now we're going to take a look at titration curves. This is where everything is combined in one, and then you test this one. Okay, yeah, no choice. Okay, so what is the titration curve? I need you all to understand some basic terminologies first. Okay, you all should know conical flask and burette. Alright, okay, but this is what they will normally say. I will titrate X against Y. What does the X and Y represent? Where is X and where is Y? Okay, so incorrect. The X, please write down, is always in the conical flask. The Y is always in the burette. Okay, let me introduce an easier term for you guys also. Instead of against Y, sometimes they will use the word with. So you must titrate the conical flask with a burette, right? Okay, with is a easier word. Sometimes they use the word against. Does that make sense? Okay, let me establish this once and for all. Okay, X against Y, the con is always conical flask against burette. They can swap the reagents around, but they cannot swap the apparatus around. So it's always conical flask and burette. Can see that first? Yeah. Okay, next. Okay, in this case, in our titration curve, later I will mention some points of interest. Okay, it's not mentioned in the notes also, but I'll just tell you all later. Okay, go over to page 42 first. Now take note, look at the title of page 42. Is strong acid and strong base. Do you think they're going to test this in the exam? No. Okay. So we cannot skip because we need to know how titration curves work first. There's a reason why I have that in the notes. Okay, guys, let's draw a graph. Okay, I'm going to write the statement. Okay, I think it's the same as the notes. Okay, you titrate HCl against NaOH. But they will always tell you guys values. Okay, against 0.1. Okay, so who's in the conical flask? Who's in the conical flask? HCl and NaOH burette. Okay, simple as that. Now, I need you to look at the axis. Axis cannot get wrong. Okay, the whole graph, you must draw yourself. It's 3 marks. Okay, what's the y-axis? Okay, you want to measure titration curves, obviously you must measure H. But what are you changing? What is the variable you're changing? Okay. Volume of what? It's always the volume of the burette or volume of the conical flask. Which one is it? You are opening the burette step, right? Okay, so it is the burette in this case, and you need. Give me your CM cube also.
I don't have time.
Okay,
it's the curve.
Okay, so this is the time. Okay, come on, look at the board. Okay, Do you start off at high pH or low pH? No. When you don't have any NaOH, you only have ACl. ACl is strong acid. Low ACl. Okay. The curve I look very carefully. Just gonna mix. Don't start me and then increase even more. This is a shape. Okay, this one is supposed to slope upwards gradually. Guys, is there a buffer for strong? No, there's no buffer yet. You just chill first. That's an easy graph. Okay? Later, we'll look at some different graphs, more important ones. Okay, because we need perform calculations on the graph.
Yeah, they're using the graph. No, on the graph.
Okay, no. Okay, can you tell me what is the pH and what's the initial pH?
1.
Okay, why?
ACl.
Good. Initially, you have no NaOH, you only have HCl. Okay, how do you find the pH of HCl? No. You just need a negative log. Because strong acid doesn't have any K, you don't have to do any log. Okay? What's the concentration? 0.1. Okay, so it's not very simple. Based on this question, it's 1.0. Alright?
Okay, how do we know 1? Why does log 1.0?
Okay, guys, as you add more and more, what happens to the pH? Increase. That one very simple. Okay, but here, what's this point? That's fine. Good. The very sharp point is called equivalence. What is the pH at the equivalence point? 7. Okay, how do you know 7? Okay, guys, HCl and NaOH, when they completely react, what happens? Okay, what's the salt here? HCl. Okay, remember from last lesson, we have to check whether this salt can undergo. Okay, we have to check whether this salt can undergo hydrolysis. Okay, remember this whole thing is a salt. This is Na plus and Cl minus. We can split it into. Number 1, can Na plus undergo hydrolysis? Okay, no, cannot. Why?
Because it is low, low charge.
Low charge. Okay, good.
Bro, you can't just take all my grade.
Okay, how about Cl minus? Can that guy undergo? Okay. No, cannot.
No, it's a big.
Okay, compared to what?
Compared to the acid.
Yes, okay, this is a strong acid. Comparatively speaking, compared to that guy only, this guy is a weak conjugate base. If it's weak, can it undergo hydrolysis? No. Can see that? Okay, what's the pH then? If both cannot hydrolyze? 7, neutral. It's not very simple. No salt hydrolysis, you can go and note down. Okay, but we need to fill in the volumes, right? Can someone tell me, right, how much NaOH do you need to hit the equivalence point? What does equivalence point really mean?
25.
Okay, equivalence point means the reaction between both species is complete, right? Okay, it's a complete reaction. Go write this down. Okay, equivalence point is a complete reaction. So in this case, in order for a complete reaction, it has to be a 1:1 ratio, correct? Okay, so how much NaOH do I need? 25. Okay, they gave you values here, and they are, how do you know 25? Okay, 25. Now it's mostly because your concentrations are equal, right? Okay, sometimes if the concentrations are not equal, you must perform mole calculations. Like go and do like extra steps. But here, because concentration is the same, the volume will also be the same. Okay, you must know this now. Then guys, after that, right, what happens? Why is it that the pH keeps increasing? What are you doing? Good, exactly. There's no more reaction any further. So what are you actually doing beyond 25?
Adding.
You're just adding NaOH, right? Okay, just adding excess base. There's no reaction. It's just going to keep going upwards. Does that make sense? Okay, this graph, there's nothing to understand. This graph, however, there are some questions for us to try. Okay, just to understand your mole calculation well enough. Okay, we're only going to try 2, and then we're going to move on already. Okay, I want to get page 44. Okay, go ahead and take a look at part A. They want you to calculate the pH at very specific points. Oh, okay, my bad. Go back.
There's no question.
Okay, never mind. Let me write this down somewhere. Okay, fine. Then never mind. Okay, let's just write down this question then. Okay, can you all calculate the pH, right? At a very specific point. The pH when the volume of NaOH is 12.5 cm. Okay, meaning to say, they want you to calculate the pH right here. Right here. What's this? Okay? How do we do this? Okay, guys, so I want you guys to write down a table with me. We already have HCl NaOH in a reaction, correct? Okay, so you get this. Okay, you can write down a little table here just to visualize your values. Okay, how much HCl is that? And we must calculate all this in terms of what? Moles. Okay, tell me what's the number of moles of HCl? No.
Oh, you do the calculation.
0.0025 moles. How much NaOH then? Yeah.
No.
Here I added 0.00125. Okay, initially don't have any of these. Okay, I don't really care about water anyway. Okay, that was next. Okay, why? Okay, good. This is the limiting reagent. You plus on the right hand side, minus on the left hand side. So guys, right now, this is the resulting solution. Okay, I have HCl and a salt. Guys, which one will contribute to the pH of the solution? HCl, because as we already mentioned, the salt is neutral. We don't really look at the salt. We don't care. Guys, that's the amount of HCl, correct? Okay, so take a look. The amount of HCl left in the solution is 0.00125 moles. But guys, I want to calculate the pH. Can you go and try? I only have number of moles, but I need a pH. Okay, yeah. Okay, hey, I want pH. No.
Take your time. Stop waiting. Answers. Fuck up, nigga.
What? Okay, guys, what's the next step after this? Nope. Okay, guys, I think this part tricky. Okay, what's next? What do I do next? Okay, I have to find concentration because that's what pH is based on. Okay, what's the concentration of pH plus? I take the number of moles and divide by the volume. What's the volume? Right?
25 times the 20.
No, it's not 25. No, it's not 12.5. It's 37.5. Guys, okay, because I think you have to realize at the very beginning, what's the volume of the solution? Not 0, because there's already 25 cm cubed in the conical flask. I didn't add any NaOH yet, so it's 25. So anything beyond that, you're just adding an extra NaOH. You can see that. This is the tricky part of titration curves. You all need to recognize, go and make a note for yourself here. Okay? Always remember the existing volume in the conical flask. So do not take the values on the graph at face value. Okay, always look at the additional conical flask volume. Once again, what's the concentration? 1.48. Okay, so yes, final answer here is 1.48. This is the concentration. With negative log and value 1.48. Answer. Can see that? Okay. Okay, of course, I can ask you guys to calculate beyond 25, before 25, all that, right, will be the same as long as you write down your table carefully, which we'll do later. Okay, a lot of it. But now, right, guys, you'll never see this again because you'll never have a strong acid, strong base titration curve. This is just for you all to understand how the basics of the graph looks like. Now, we're going to proceed over to that page. Okay, what page is it? Okay, 44, I think might be different. Okay, so here we'll be looking at a weak acid strong base. Go ahead and maybe start this page because this is what you had. So now they're going to use a weak acid against a strong base. CH3CO2H, titrate it with NaOH. So take a look at the statement. Okay, this is the statement here. Let's redraw the titration. You're going to draw the axis. Now, what's the axis?
Why?
It's still pH, x-axis is. Okay, volume of NaOH. Again, NaOH is still in the burette that has not changed. Okay, I want you all to look at how the shape of the graph looks like. Okay, be very careful here. Next page, is there any questions for you to do? Just in case. Okay, have. Okay. Come, take a look. How does the graph look like? Do you start off high or start off low? Low. Okay. It doesn't really matter because we don't have the previous graph to compare. Let's start off at the low pH because it's a pH of the what? The acid only. Okay, so acid must have low pH. Okay, look at my shape. Okay, come look at the bottom. I will go up first and then it will start to flatten and go up then normally. The only change between this and the one just now is that here it will increase very slightly before it starts to flatten out. Okay, later we have to. Okay, the first graph in comparison, it was just an increase. Here it increased a bit before it flattens. Any guesses? Any preliminary guesses? No, it doesn't. Okay, yeah, something like this. Hey guys, any idea why? Why it starts to flatten? What kind of solution, right? Is it that the pH is constant? Buffer. Okay, there will be a buffer somewhere later. I'll explain. Okay, so this is the shape of the graph. Not completely straight, but it doesn't really matter when so yeah, okay, it's ish. Not really lah. It doesn't really matter. Just give me a sharp increase, can you? You make it very vertical, who cares, right? Okay, so guys, take a look. Take a look. Okay, what we're gonna do right now. Okay, let me draw this. Okay, I will now go into the specifics of every single point. We're gonna start from the left and move our way towards the right. Okay, guys, I will start off at the left-hand side where you haven't had anything yet. This is the initial pH. Guys, how do you calculate the initial pH? No, cannot. Because here, this is the pH of a weak acid. You can weak acid just do negative log. What is minus? Between these three question types, which one is it under? Weak acid. Okay, it's just the dissociation. Yes. Okay, so I need you to take note. Initial pH is the dissociation question type. You're gonna write it like somewhere else. Okay. Why is that the case? Because I need you guys to always, in order to identify the correct question type, you must ask yourself what species is present right here. So under initial pH, I need you to ask yourself what is the species present here? How many species? Two. No, at the very start. I only have CH3CO2 here. Okay, so go write it down. I only have CH3CO2H, which is a weak acid, and a weak acid must undergo dissociation. Over here, you can see that. This is how you identify the question type, because the moment you identify the question type, you will know what your calculation steps are. Okay. Guys, how do you calculate this? Okay, yeah, because to do pH, if you want to do negative log H plus, and the H plus, you just take it as face value 0.1. Is that correct? Is this the concentration of H plus? It only partially dissociates. So your H plus must be a lot smaller than this. So you can't just do this directly. Now take a look. I want you all to write this in your that question. Okay, you all turn over to the next page. I think it's page 46 or something, right? You all see a few questions. Okay, write it down over there. The first question is asking you guys about initial pH. Can you all see that? They want you to calculate the value. So write this down over here. Okay, what page is that? Because mine different already. 46. Okay, 46. I'm going to write it down. Later, I will come back to the graph, then you will edit the graph. Come, how do we calculate this value? Nope, that is buffer already. I'm not talking about buffers at all, right? Sorry? Yes. Okay. Come. There's a short way. Okay, before you okay, I want to write down two things. The method we were taught and then a shorter version of it. Okay, so I'll teach you all the shorter version because it's way faster. Okay, first of all, the long method is CH3CO2H dissociates into its conjugate base and H plus, correct? Now, let's do an IC table. Can you fill this up? This one is? It is 0.1, right? We surely haven't dissociated. How much dissociated? X. Okay, correct? X. Okay, then what's next? Yeah, correct. All these equilibrium values, where do you substitute it? Okay, the Ka expression. So Ka is equals to x squared over 0.1 minus x. But we have to assume it to be just 0.1. Okay, then you equate this into the K value, which they will confirm give you one. In this case, they gave us 1.8 times 10 to the power minus 5. Can you see that? And what do you solve for? Okay, what does x represent though? Equilibrium. X represents the H plus after the dissociation, which is an equilibrium. Go and find that, and then go and find the pH value. That's how you perform the dissociation calculation. Is it difficult? I really don't think it is. Okay, the most important part here is not the calculations. I don't care about that. They're all your own.
So we use this formula and that's a weak acid.
Just a weak acid. But you identify the dissociation of this. Okay. Answer the top, right?
Like, yeah, bro.
Yeah, you'll get 2.87.
Bro, I'm gonna get sick, bro.
Okay. Eventually, guys, you all notice this IC table. Is it very useful? Honestly, it's kind of useless, right? Let me show you guys for dissociation that is a shorter method to go straight into H plus. Okay, come on. From here, I'm only interested in H plus. Right, that's like the most important thing. Okay, so give me your H plus. If you realize, right, is you just to find X, you take Ka times the concentration of the acid. Please square root. You can see that. Okay, I'm just like making it easier for you guys out. You take Ka, multiply by the concentration of the acid, square root the whole thing, and you can get it. Then you can find pH. Okay. Now, guys, this is nothing special. It's just this, but without the IC table. That's it. So from now on, right, for dissociation only, please use that one. It's way faster. 1 mark if you get it in an instant. You don't need to tell me you assume the X away and all that nonsense. Okay, very useful. Now then you give us what? 0.1.
Because we take a minus.
Okay, guys, can go back to the graph. I need you all to label this as 2.87. Graph must label one. If you don't label the graph, they also penalize, right? Okay, 10. Now let's proceed to the second part of the graph. Do you all still need this? I think it is. No, okay, here, can you tell me where's the equivalence point from? It's right here, but there is something before this equivalence point, which is in between the start and the middle, right? Okay, here we're going to discuss the pH before the equivalence point. This is the second point of interest. Okay, remember, guys, to identify which three of the question types, you must tell me what species is right there. Okay, now, okay, actually, before that, since the big buffer here, right, I want to go straight to the middle first. What is the pH at the equivalence point? So, guys, for the question on the next page, right, on page like 46, okay, go to page 40. Go to part D. Cannot find part D. It says that pH equivalence point. That straight, right? It's one whole page long because there's a lot of things to write.
What's not so big?
Okay, can you see that part D? Okay, right there. Okay, so I'll tell you first. Okay, I want to deal with the equivalence point pH right now. You must tell me what species is at the equivalence point. Tell me. Take note, there's a complete reaction between this guy and NaOH. So okay, tell me what is the species present.
VH. VNO2 minus N1.
Yes, okay. You have CH3CO2H plus NaOH. And here, since it's a complete reaction, I only contain a what? Acid plus base full reaction must only contain a salt. And the salt in question here is CH3CO2 minus. Can you see that? Again, that means at this point, you have nothing else. You only have one species of salt. Does that make sense? Okay, go write this down. Because CH3CO2H at the start reacts with NaOH to give it. Okay, this is the equation if you want to know. CH3CO2H plus NaOH to give this. CH3CO2 minus Na plus and water. I don't care about Na plus because Na plus does not hydrolyze. So guys, what kind of question type is this?
Hydrolysis.
Okay, you only have the salt, but this salt can undergo hydrolysis. So we'll identify the question type at the top also. You can write it down, salt hydrolysis. You see that?
So, like, is it a equivalent point for a weak base and strong acid? Is it usually like?
Yes, okay, so from now on, if you want to find the pH equivalence point, you must employ salt hydrolysis method. Okay, we are done with dissociation, we did salt hydrolysis. Okay, let's perform our calculations right now. Okay, how do we do that? Guys, remember our salt hydrolysis. Okay, I'm gonna write down the steps. For salt hydrolysis, what's the first step? I always must see the equation. So give me your salt hydrolysis equation. Practice the whole of the last lesson. Okay, so guys, what is the equation here? Craft the equation for me. Okay. What arrow first, by the way?
Full arrow.
No, it's the half arrow. Reversible because it's this neutralization. No, it's hydrolysis, right? Okay, what do you get?
CH3CO2H plus OH.
Very good. You must come out with this first. Okay, what's the second step? Okay, every time you come out with equation, I follow it up with a table. IC table. Okay, can you all feel the values here?
Wait.
Okay, what is the does water matter?
No.
Okay, we get that out first. What's the initial concentration of the salt? What's the concentration of the salt here?
Is the acid.
Is it 0.1? No, it's not. In fact, this part over here, this one like helps it out. This is the key part that we okay, we will explain.
So it's like half reacted already.
Yeah, you're true, right? Okay, but we'll get there. What is it half? Okay, come. Look at this. Guys, this is the concentration of the salt. Now, okay, what I want you guys to do first to make your life a bit easier. For salt hydrolysis calculations, very tedious. So for the table, I need you to memorize as minus x plus x plus x. Everything here is similar to dissociation. Okay, everything here is similar, just write it down first. Okay, so this is one of those few times, right, where I'll ask you guys to just memorize the IC. The only thing you need to calculate, right, is this. What's the concentration of CH3CO2? Now, guys, in order to find concentration, let's go back to our roots. We take number of moles divided by volume. Okay, first of all, what's the number of moles of CH3CO2 minus?
0.195.
Yes, can you all see that, guys? Since this is a complete reaction, what's the mole ratio? 1:1, even here is 1 as well. So can you all see the number of moles of the salt is the same as CH3CO2? Complete reaction, you can see that. So whatever CH3CO2H is 0.0025 is equal to your conjugate base also. They are both the same 0.0025 moles. Can you see that? Okay.
Oh. I know.
Okay, and guys, we found concentration, you must divide by volume. Okay, what's the concentration of the salt?
0.1.
You take the number of moles and divide by. What's the volume? What's the volume at equivalence point? You guys ask yourself first, how much annually do you need to add at equivalence?
25.
Okay, see our 1-to-1 ratio, right? Okay, so you also need to add 25. So what's the volume over here?
50.
50. Because you have 25 from the NaOH and another 25 from the where? From the initial conical flask. That's why it's 25 plus 25. The concentration here, like what Hakim said, is actually half of the initial concentration. 0.05 mole per dm cube. And that's the value that you should put up here. Because the concentration of the salt cannot be the same as initial. Because this one, right, the volume is different from now. You can see that?
Yeah.
So this is a very tricky part. I want to put it as part of the steps. But it's just something you need to figure out along the way. That's why this is one whole page, very tedious. Okay, so far. Now we have finished up the IC table. Where do you start this IC table into? Okay, you start all the equilibrium into where again? Sorry. Huh? Guys, do we use Ka or Kb? Kb. Why? How do you know Kb? You produce OH minus, it must be Kb. Guys, remember what's the third step? Did they give me Kb in this question?
Oh, you find it yourself.
Okay, how do you find Kb if they only give me Ka? Kw is equal to Ka times Kb. Use this to manipulate. Okay, let's continue right here. The Kb, go and find it first. And then you substitute the equilibrium values into the Kb, which is pretty much just this. Can you see that? I immediately get rid of the x, the quadratic. I just do that very quickly. Go and find the Kb value also. Solve for x. Yeah, continue here. It's very, very tedious. Ask yourself what x is, but eventually you need to find the Kb. Very tedious. So I need to practice. For the first try, you won't get it. 3 tries later, you probably still will struggle a bit as well. Okay, this one needs practice. Okay, go work it out. Perhaps in the steps, I need you all to write this down. IC table. Find the concentration of the salt at equivalence.
Thank you. 8.7. Yeah. Ah. They like read everything. You like everything. Probability. What are the probability? What are the probability? Look at how he's speaking. Who is that? Straight up and what? Oh, what did you like?
Okay, all good?
Yeah.
All right. Okay, so what's the final answer? 8.7. Okay, good. Go and find POH first, then go and find pH. Very tedious, as you can see. Right, that's for salt hydrolysis. Every time they ask you to calculate pH at equivalence point, okay, it's not as easy as this. Okay, so guys, even if you never do calculations, right, the pH here must be above 7 or less than 7. Okay, based on this equation here, the salt hydrolyzed to produce more OH minus, right? So that's why it has to be more than 7. And your answer here is indeed more than 7. So that label on the graph as well. Can you see that?
14 minus.
Okay.
I'm pretty sure there's no 8 minus. This X is literally not 0.001.
Wait, right.
And that's why I don't know.
Okay, come.
Oh, you can't do this with this thing. Okay.
Okay, we skip part B and part C. We go back to part B also. Okay, I want to discuss the middle segment that we have not discussed yet. Right? Okay, come, take a look. Okay, part B. They want the pH when the volume is 12.5. How? Okay, so let's figure out first what species are at this point. Okay, so come. pH before equivalence for part B. Go write this down. We have to identify what question type, correct? So in order to identify this, let's come up with the equation first. CH3CO2H plus NaOH gives me the salt and water. Okay, I'm gonna use an ICF table to figure out, right, what are the remaining amounts if I only had 12.5 cm3. Okay, how much acid do I have at the start? Okay, I'll do this in moles. How much acid do I have at the start? 0.0025, right? How much NaOH do I have? Okay, 0.00125. Can see. Okay, initially I don't have anything. Then what is the change?
0.00125.
Okay, limiting. Get rid of it. Okay, we have to do all this. Just now I didn't do it for complete reaction. Because we know complete reaction just means 1:1, so it's pointless to do all this. But right now, I can do all this and figure out what are the resulting species. And what is my answer here?
Acid and conjugate.
Exactly, guys. Do you notice after you add 12.5 cm3 and after the reactions, I will have an acid and a conjugate base. Can see that? I have both acid and conjugate base. What does it mean?
Conjugate is a buffer.
Okay, I will have a buffer. Good. Let me write this down. So guys, can you see? This first part of the question is just for me and for us to figure out what calculation question type I'm supposed to be with. See that? Now, before I move on to the calculation properly, can you tell me, right, where is the buffer region? It can't just be at this one point over here, right? Where is the region at which the buffer can occur?
Okay.
All the points?
Okay,
good. Tell me the range now, guys. At 0, do we have two species, conjugate acid-base pair?
No.
At the equivalence point?
No.
Also don't have. But you all notice, right? At any point between 0 and 25, okay? At any point between 0 and 25, my strong base is limiting or excess.
Strong base is limiting.
And we did this the last lesson as well. This is a very fast way of determining whether there's a buffer. Can there be any strong species in a buffer? No. So it has to be limiting or excess? Limiting. Between 0 and 25, it is limiting. Hence, we can tell definitely that this is the buffer zone between 0 and 25. Can see that? So it's not just 12.5. 12.5 just happens to be right smack in the middle of this region. Okay? And guys, this table, right, I can tell you is super useful. Because right now, how do we calculate the pH of a buffer? Is there an equation that I can use? Okay, what's the full thing? Okay, buffer, you take pH equals to pKa plus okay, log conjugate base over acid.
Exactly.
Come, let's sum in the values. What's the pKa here? Go and find, okay, go and tell me what's the pH.
This is the 1.
Which one is 1?
No.
Good. Okay, do you all realize that my acid and conjugate base is equal?
Maximum.
Good. Okay, look at the board first. Don't calculate yet. Very important. Do you all notice that the acid and conjugate base are equal?
Yeah.
So actually, to simplify this equation, it's just pH equals to pK. So in order to find the pH here, just tell me what's the pK value. What's this concept again? Good. Go and note this down. I'm not really interested in the answer here. What I'm interested in is the shortcut. If you see this, the both species are equal. Can you tell me what you observe about 12.5? What's so special about 12.5? It's exactly half of the equivalence, right? So from now on, right, I need you to take note. The half equivalence point generally is the maximum buffer capacity. I say generally because later we'll look at one exception. Go write this down. So next time when you all see okay, this value here, right smack in the middle, half equivalence, you and identify it immediately its maximum buffer. Meaning to say you can just pop out this equation and that's it. So what's the answer? Go and find for your pKa.
I didn't find pK.
That's negative log the pKa, right? P stands for negative log.
Oh. I'm feeling. If you do this for the past 1 week, go inside a meatball. It's a no. You're like me. You're actually me.
Okay, part C, okay guys, at this point, I've taught you all three pressure types and we're going to locate them in a titration curve. So part C, look at part C first. It's one of the three pressure types that I identify.
Part 2.
Okay, so now any questions with part B first? No, answer here 4.74. I need you to label the graph. Okay, so 4.74. Okay, on the other hand, what's part C asking for?
Why?
Okay, now they add at 20 cm3. What is this question type? It's still in the buffer zone, right? You can see that. So now our job is to identify what is the pH at 20 cm3.
Okay.
Go and find that. Remember, use this table, very useful. Okay, what happens when you add 20 cm3 of NaOH? Fill this table. Okay, so I can summarize the steps. The first step for buffer is a equation. I need to see a neutralization equation first. You can see that. Neutralization because that's what exactly this titration curve is doing. Okay, second of all, I need to see an ICF table. Okay, take note, this ICF table must be done in moles because you're adding stuff and then you got to calculate concentration here. Okay, last but not least, like what we did just now, substitute to the Henderson equation. Okay, go and try. In the table, right? The acid is 0.0025, base is 0.0020, right? Okay. Because they add 20 cm3. limiting reagent is still the strong base. Can you all see it? If the strong base is still the limiting reagent, which happens within this zone, that means you will eventually still get A plus one. Okay, you have a portion of acid and conjugate base. So how should we do this? Right. Okay, come calculate the pH. Okay, hope you understand the essence of all this. Okay, every calculation type is in a titration curve. You must identify the type first. If not, you end up doing the whole thing wrong. Okay, no point. Those who are done, right, you can try part E actually. Part E is not very important. Okay, but they can still test part E. Alright. Ooh. I can you read it? Huh?
I think that
Oh, part C there. Oh, okay, yeah. To part E. Okay, can get the final answer here. Right, buffer, we still can use P equals to pKa plus log, conjugate base on top, so 0.002, acid at the bottom. Remember, you must divide by the volume as well, just for working sake. Because these are in concentrations, but your values here are in moles. So just divide by V. It will eventually cancel out, so it doesn't matter. Answer here 5 point something. Okay, the volumes are the same because they are in the same container, so it doesn't matter. Yeah. Answer here is 5.35.
So can you just write V or?
Yes, you can just write V. Okay, we're fine with this. You can look at part E. Okay, this one I'll just quickly go through because we still have a few examples to touch on. Right?
Wait, the K you need to convert to PK.
Yes, correct. Okay, anyone have any questions? Part A to part D is like the most important part. Basically, when you revise, I want you to take out this set of notes, right? Redo part A to part D yourself. Okay, then we look at part E. Okay, part E is asking for the okay, it's asking for a 30 cm cube, which is beyond 25. That is the final set, the final interest point over here. Okay, we want the pH after equivalence point. Okay, we have to identify first what is the species present at this point.
That's the base.
Okay, what base? Okay, beyond 25 cm cube, is there any further reaction? No. Okay, so you only have the salt, right? Okay, so the species present here, I have the salt, CH3CO2 minus, and what else? Okay, you're just adding excess strong base, right? Okay, so you're adding excess NaOH. Guys, which one do you think, right, will contribute to the pH of the solution to a larger extent? NaOH, good. Okay, compared to NaOH, CH3CO2 minus is much bigger. Okay, take note, NaOH is objectively a strong base. Compared, CH3CO2 minus is bigger. So we don't actually care about CH3CO2 minuses pH or pOH in this case. Okay, we're just taking a look at NaOH. See that? Alright. So to calculate NaOH, it's just that's pretty much it. Right? Okay, there's no question type here. Okay, I want you guys to find the concentration of OH minus in excess. That's pretty much it. How much when you add 30 cmP of NaOH, how much of it is actually additional extra? Okay, if you add 30 cmP of NaOH, it's all 30 the extra. It's just 5 extra, right? You can see that. Okay, so I'm going to find out what is the number of moles of OH minus in excess. It is 5 cm cubed, then you must multiply by its concentration. You can see that. So it's 5 times 10 to the power minus 4 moles. Or what am I interested in? Number of moles must convert into concentration. So I find the concentration of OH minus in excess. So I must divide by what? What's the volume?
Volume is 30 plus 25.
Good. Okay, 25 from the conical flask and then another 30 cm of NaOH. Use this to go and find the concentration of OH minus. And from that, I'm sure you all know how to find the pH. Yeah. Okay? Okay. So final answer here.
Wow.
Okay, 12.0. I need to see PS7. Okay, all good. So you have practiced one whole set of calculations. Imagine they will ask these 5 parts in one exam question. You have to do everything.
But will we be like similar type or will we be?
Similar type. Yeah. Okay, it's really just training you guys on the calculation technique only. Okay, we're gonna look at the next page. Alright. It's now we're gonna look at different variations of the graph. We're not gonna perform the same calculations again because they're all similar. Alright. Okay, so I'm going to draw the axis for the next graph. Let me present another scenario, very similar. Okay, so instead of a weak acid and a strong base, they now take a weak base and a strong acid. Not much of a difference, but honestly. Okay, weak base here, I'm just going to use HCl is a strong acid. Come up, when we look at this graph, how does the shape look like? Okay, tell me what's the axis first. Okay, what's the axis?
pH.
pH against
Volume.
volume of
Volume of paint.
how what?
Only
Okay, volume of the what? Volume of the what?
HCl.
Okay, good. Okay, HCl is your period up once again. 35. Okay, with that said, where does the graph start at? Top. Okay, high pH. Okay, guys, remember how the graph looks like? It starts on top because of the base. It has to drop first before it flattens out, and then everything else follows. It's a mirror graph of just now. Now, can you all answer maybe this question right now? Why is there a slight drop before it starts to plateau?
Because I
Buffer, correct? Now, at the very start, do you all remember? Do you think the ratio of the acid and conjugate base at the start is very high or is it very balanced? Okay, very skewed or is it very balanced? At the start over here, when it just started. It's not balanced, right? You can see that. Remember we mentioned just now the concept of effective buffer rate. Your ratio of acid and conjugate base should be as close to what? What's the best? 1:1 as possible. Remember, where is the 1:1 ratio? In the middle, good. In the middle right here is your half equivalence point, which in this case is still 12.5. Equivalence point is 25, right?
How do you know that? Oh,
I'm using the same values as just now. Oh, yeah, again 25 and 0.1 move per cube. Okay, only in the middle right here, then the ratio is the most healthy at 1:1. But at the start, right, the ratio is barely even in the acceptable range. That's why the pH is not getting resisted. Okay, can? Maybe a 0, 25, and your 12.5, whatever. Can someone tell me where's the buffer region again? Okay, between 0 and 25, because guys, always ask yourself, what is the test? What's the test here? How do you check? Whether the strong species is, let me think. Okay, guys, ask yourself, between 0 and 25 in this graph, is strong, in this case, it's a strong acid. Is it limiting for a test? Okay, good. You see, your base is 25 cm3. Your acid must be anything less than 25, agree? Which is anything less than 25 here, this region. So the strong species HCl is limiting. And as a result, that's how we determine that this end of the graph is the buffer. Okay, good?
yeah.
Okay, I know we're not performing much calculations, okay, but it's actually very possible to go through. Okay, I'm not going to do the calculations, and instead, I want you all to tell me what are the species at each point. So guys, go write this down somewhere. When the volume of HCl is 0 cm3, what species are present? Anything else? At 0 cm3, what species are present or is present? No, okay, there's NH3 only, so write it down. So what question type is this? Come tell me. Okay, weak base dissociation, good. Okay guys, let me just give you a random number. When the volume of HCl is at 8 cm3. How do you know that? Okay, it's within the buffer range, yes. And most importantly, to figure that out, it is, the strong species is limiting. Okay, that's the shortcut here. Okay, so what are the species present? And good. Why is there no HCl? I thought I added HCl. Because it's limiting, right? It reacted away, it produce what you want. Agree? Okay, so you have buffer solution. Apply your buffer steps at one level. Okay, next. Volume of HCl, 25 cm3. What's this? What species? Okay, 25. You're going to solve hydrolysis. Why? What's the species called in this case? What's the salt in this case? Okay, good. We need to know that 25 cm3 is the equivalence point. You only contain the salt NH4 plus, so it's a salt hydrolysis question. Can you see that? These are the basics. The calculation you're going to do yourself. No, I really don't care about that. The long term. Okay, what I really care about, right, is your identification. Can so far? Yeah. Okay, I won't really go beyond that one. No question type. Can? Okay, just one more lah. What volume of HCl at 12.5? Can someone just calculate the pH at this point? Additional one. Come, let's try this. Okay, come, go and tell me what is the pH at 12.5 cm3. Okay, I don't want to see a lot of calculation because I already told you all what the concept is important. I'll go up to my little bit skewed. Try to take the plug point in the middle instead. Never mind, I'll just practice the other way. Guys, how do you calculate this? Okay, PKP, right? How do you get to this conclusion? Okay, and 12.5 cm cube, what's the significance? Okay, MVC, what's the formula? Okay, it's a half equivalent, so it's MVC. Yes, correct. Go write that down. So, what's the formula here? Okay, this one is a base, right? So assume the question gave us K. So what do we use? If you want to use KB, go and find POH, but at the end of the day, go and find the pH of the solution. Okay, I don't know whether they gave you the KB values, okay, but this is the step. Okay, so the KB of NH3, right? Let me just tell you all first, is 1.8 times 10 to the power minus 5. Yeah, so let me calculate what's the P. Okay, but I also don't know what it is. Okay. Okay. 9.5. Yeah, okay, what's the POH? POH is 4.74, right? So the pH is? Yeah, okay. Very fast, no calculation needed, as long as you know your concept. Okay, so far. We're looking at a final graph now. Okay. Any questions? Good luck. Can you all take a look at page 5? No, my page is wrong already. Okay, draw the axis debate. Thank you. Yes. Okay, come, draw the axis. We're gonna do the same exact thing, huh? Okay. Strong acid against weak base. Strong acid, I'm going to use NaCl. Weak base, NH3. Now note this, how I'm just swapping the positions of the reagents. Okay, cortical plus period, I just swap it. Okay. Some of you will say, what's the difference? Okay, so come. Graph first. Okay, pH against what? Okay, look at what you're adding now. You're adding the weak base. Pay attention to the swap order. Where do you start the graph from? Low. Okay, low, and then low because it started off with ACL. Okay, very simple. Now look at the shape of my graph we will discuss. Yeah, it's just an S. Okay? Now I'm going to give you guys the same thing. I'm going to tell you all the possible points, and you need to tell me what species and what question type. So guys, what happens when the volume of NH3 is at 0? Okay, good. You only have ACl. Okay, yes, acid can dissociate, but you need to do all the formula Ka. No, okay, in this case, HCl is a strong acid, you can just use what formula? Negative log. So that's not, okay, when we say the word dissociation, let's just for now on assume, right, it's for weak items. Okay, but yeah, really good. This one can just use negative log H plus. Can you see why? Dissociate is completely, right? Okay, in this case, I can even calculate it right now. 0.1 means if I go negative log, the value is just 1.0. Okay, not very important here. Guys, next. Can you tell me at volume at 25 cm cube, what's this? Good. What are the species present? Okay, anything else? Okay, equivalence point is at 25. So I only have the salt, which is NH4 plus. What fraction type? Salt hydrolysis. Okay, again, the techniques and all that you need to hone over time. My job over here is to help you identify all this first. Okay, next. Volume of NH3, 15 cm cube. Just tell me what the species first. Okay, tell me the species. I don't care about what question type first. You must identify the species. The question type will come afterwards. Okay, ask yourself first. Okay, this is where things are a bit tricky. Is a strong species limiting? No. You all notice, right? When we sort the order, my strong species is 25. My weak base is less than 25. So in this case, my strong species HCl is in excess. Put in caps, this is very important. You see, this is one of those situations where they can swap the order and then your treatment becomes different. So to identify buffers, don't just anyhow assume strong is limiting. Here's excess, so guys, really a buffer. No, this is nothing. Can you tell me what the species here first? NH3, sure. NH3 is limiting now. Okay. So I have NH4 plus and HCl that is left over. Is this anything? Nothing. But with that in mind, can someone tell me where the buffer is? After 25. Because after 25, you all can see, you can pick any random value. Okay, let me just pick 30 cm cube. When the volume of NH3 is 30 cm cube, the HCl is 25. It's a strong limiting in this case. Yes. Strong HCl limiting. Meaning, guys, this is one of those rare cases. With this part over here is about what are the species present? Okay, correct. NH3 limited. NH4. Or NH3 left over, my bad. So this buffer. I'll go with this. You see, okay, this is the spectral graph. More often than not, the buffer will be on the left hand side. Here's this case. I'll ask one more chapter, and then we're done with this graph here. Yeah, write down this question. I think it's even in the notes. Yeah, I don't know. You all flip a few pages. Yeah, it's right there as well. The next box. Yeah, correct. What page is that? Okay, 54. Okay, go to 54. There's only one question there. I need you all to answer this question. Where is MBC for this graph? Think on. Okay, let's discuss that. Where do you think it is first? Maybe you all have your first thought, your first intuition. Okay. What volume do you have MBC? Is it still at 12.5? No, okay, ignore this whole part. It's not even the region, it's not even buffer anymore. It has to be somewhere above 25, but where? That's the question. Okay, just now we said 12.5, right? 12.5 is half of equivalence. So, what's a possible answer on here? Okay, some people will say 37.5. Okay, that is the first answer that a lot of people will think. But let's see whether this is correct. Okay, I want you to the box very big, right? A lot of space. Okay. Wait up. Come. Why I say 37.5 is because that's the first guess. A lot of people think half equivalence and now 3/4 equivalence. Look, at 37.5, the reaction is between HCl and NH3. Same thing. HCl and NH3. Go write this table out. Okay, look. A, I, C, and F. Guys, what's the initial amount of NH3? How much NH3 am I adding here? If you tell me 37.5. Wow. Okay. 0.00375, correct? HCl is how much? HCl is in the conical flask. The conical flask is 25. Initially 0. How much do I minus here? Limiting, the strong is limiting. Okay. Okay, so you fill in the table already, you fill the math. Is this the MBC? Why? Why not? It's not equal. Okay, good. Remember, this is not MBC, I need you all to write down. Okay. 37.5 is not the MBC. Okay, as from the table above, the concentration, the amounts of NH3 and NH4 plus are not. They're supposed to be what? Yes, okay. They're not even equal here. If they're not equal, it's not MBC. So with that information, how do you make it such that both of them are equal? Yes. So you might want to change the table or write down another table where I put how much NH3? 50. Because if you try 50 cm cube, you minus 0.0025, you will still get 0.0025. This is where it is equal. So go write down. MBC here is what of the equivalence? 2 times of the equivalence. Good. They might ask this question. A lot of people will take it's either take very long to think of the answer, or they will just give me straight 37.5. Because you run out of time, and then just try to make an answer. No, it's 2 times. So volume of NH3 will be 50 cm in this context. Okay, then. Yeah. So this is the unique graph. Just pay attention to this. Oh, good. Right. Just a bunch of things to go through before we end off for this chapter. Okay, I'm pretty sure we can finish this by the end of the lesson. Okay, that's good. Right? Okay, but let me tell you first, at the end of the lesson, I need to give you homework for this. Must have homework. And then you must, after do already, send me. Okay.
Oh, that's not go through.
You send me, then I'll give you feedback on the answers. Okay, because we have no time. Next lesson, we have to start on alcohol. Alcohols. I don't see alcohols.
So we prior.
Yeah, I mean, hopefully it's okay. Actually, it's no need. It's best to invest. Okay, any questions so far? Guys, we still have one more small little thing to go through. Okay, page 57. No, my page is different. Sorry. Next page is polyprotic acids. Do you all know what that means?
Oh,
that's monoprotic. Let's take a look. Okay, then polyprotic acids. Give me some examples of polyprotic acids. Okay, it's HCl or polyprotic acid.
Oh.
Okay, that's monoprotic. Okay, what are some examples? H2SO4, H2CO3, H3PO4. Okay, these three are like the most common ones. We're gonna understand the concept after this, right? Okay, you see the box, we skip this first. I want you to go to the next page where there's a graph. Now, in this exercise, we're not going to do calculations, but because I'm going to look at H3PO4, these guys have multiple equivalence points. So you're going to have multiple sharp curves on your titration graph. Because there's so many curves, it will get confusing. So I need you all to be able to weave through this confusion by identifying all the species at different points. So guys, take a look at the graph on the next page. It's already drawn for you. Okay, and this is my exercise to you guys. They add NaOH to the H3PO4. Now guys, I'm going to use this as a little, what do you call it, reference. H3PO4 dissociate once, then it dissociates the second time, and then it dissociates the last time. It can dissociate 3 times because it has 3 H's. 3 H's obviously can dissociate 3 times. Now, why this is difficult is because there's so many goddamn species. And then the graph is so many different points. If you identify wrongly, the whole thing is wrong. You don't even need to bother about all this because it's wrong. Okay, so look at the graph. I don't really care about the values. Instead, I want you to tell me, right, what are the species present at this point? Okay, actually, right, guys, they added 20 cm. Okay, never mind. Later we'll talk about this. Okay, I want you to do the 10, 0, 10, 20, 30, 40, 50. Okay, 50 ends for there. Okay, this is what's printed in the notes. And what I need you guys to do, for every single 0, 10, 20, 30, 40, 50, right, go and identify what species is present. Okay, yeah, okay, that's what I was trying to say also. The other things, right, actually, how much NaOH is needed for complete reaction? So you react 3 times. Okay, guys, yes, correct. So I want you to draw in the graph also. Okay, so just follow me. Where is the equivalence points? Always identify equivalence points first. Okay, sharp points. Okay, please look at that. Okay, for this kind of questions, always identify the equivalence. Now take a look. On all these equivalence points, how many by right you should have? How many equivalents? 3. The first equivalent requires 20. Second equivalence also requires another 20. The third equivalence, where should you be ending? 60. So I want you guys to kind of extend it until you. So that right there is the third equivalence. What I want you guys to do, with reference to all these species, tell me what are the species at 0, 10, 20, all the way, 30, 40, 50, 60. Give me everything. Let me give you a clue. It's better to do the equivalence points first. Okay, do the equivalence points first. Okay, there's a box at the bottom. I'm just going to write it down. Right. Okay, done. Yeah. Get at 0 first. Okay, I suggest do the 0 and all the 3 equivalents. It's a lot easier. Okay, some of you are a little bit stuck. Okay, let's go over this first. Guys, at 0 cm cube, what are the species present? It only have H3PO4, nothing else. Alright, then only. Okay, guys, we go to the first equivalence. And the first equivalence, what should we have?
H3PO. Wait, first equivalence.
Okay, guys, at the first equivalence, you must completely turn this into
H2PO.
H2PO4 minus the first conjugate base that it has. So put this under 20 cm cube. Only H2PO4 minus. How about the second equivalence at 40?
It will be PO4.
Yes, in the other species. Remember, at all your equivalence points, you only contain the salt. These are the respective salts. How about the what's next? You have the third equivalence points at 60, which is the last one, only PO43 minus. Now, there's a reason why I always ask you guys to identify equivalence first. Because everything else in between, can someone tell me all these 10, 30, 50? 10, 30, and 50. What are these regions here? They're all buffer regions. So how many species must you have in 10, 30? And yes, you have 2. What are the 2 though? That's the thing. In the 10 cm cube, essentially, you cannot see a sandwich between 0 and 20, right? Those are the 2 species. Right? Can you see that? Okay. It's literally sandwiching between these 2. So we're going to tell me H3PO4 and H2PO4 minus. Okay, guys, this exercise is very important because in the exam, if you don't know what species you're dealing with, I can't help you. Right? Again, 30 cm cube is in between 20 and 40. Sandwich them together. Last one, 50 cm cube is between 40 and 60. Just give me 40. Oh, it's already ready. Oh, good. Any questions? Yeah. Okay, one final thing, which is honestly like not even it's not even important. And then skip it. Yeah, we can't skip it, you still talk about it. It's very easy to get 3 marks on this. Indicators.
What is the name so big? Indicator they won't get memorized.
You need to memorize a few, yes.
Graphs. Let's see.
Okay, guys, come. Last one already. Can we go over to the last segment? Acid-base indicators. Okay, can you all just highlight that box over there? When you justify an indicator to use, you just have to tell me it coincides with the rapid pH change of the titration. That's it. Okay, or whatever indicator you use, you're repeating the same justification. Okay, so let's explain a little bit. Guys, in a titration curve, what is the purpose of an indicator? Is to tell you when the titration should stop, right? Guys, where should you stop the titration? At the equivalence. So guys, it makes logical sense for the indicator to only work at the equivalence. Can see that? Indicator tells you to stop. Where to stop is the equivalence. So the indicator can only function well at this range where the equivalence point is. So look at the formal definition. The working pH range of an indicator. Basically, different indicators got different ranges. You must choose the one with the range that coincides with the equivalence pH. Okay, it must coincide. So it's very simple. Guys, if right now my pH at equivalence point is 8.27, which one of these indicators should I use?
8.27.
What are some possible indicators? Look at the table. Phenolphthalein or thymol-blue. Exactly. What if my pH is now 4.2? Green now. Okay, pinta orange, or yeah, that's pretty much it, right? Guys, I need you all to only take note of 3 indicators. Beta orange, go and memorize the color change. Like phenolphthalein, memorize the color change also. Finally, thymol-blue. Now notice, beta orange is for what kind of equivalence points? Acidic equivalence points. How about phenolphthalein and thymol-blue? I give you 2 options because some of you cannot spell the first one. Okay.
Wait, -1.
Minus 1, yes.
Basic.
Okay, it's for basic equivalence points. Okay, guys, that's it. Okay, guys, listen up. They will ask you what indicator to choose. You choose based on acidic or basic equivalent. Then the next thing they will ask is why. Guys, why is because of this shit here. Just repeat whatever they say in the box. That's it. That's it. Okay. So guys, can you all take a look at the final page already? Final page. Okay. Guys, in the final page, don't need to write the answer. You all just verbally tell me the answer. Come look. Okay, guys, what indicator should I choose here? Okay, why? What was the reason? Verbally, just tell me. Oh, yeah, pretty much. Yeah, that's it. Bloody yeah, guys. Guys. Guys, if any of you get this question wrong in exam, and I see I'm gonna plug your whole sack out, serious. Okay, and sometimes it give me marks. Yeah, okay. Later it's gonna start to be wrong on purpose. You get wrong on purpose, you plug your whole sack out, right? Okay, cannot, in some basket of marks. Yes. Okay, we are pretty much done for today's lesson. Guys, I will have homework for you guys. I don't have a deadline because this is my policy. I believe you all are cool enough to tell me when you're done with your homework. You're done, you just send me. If you don't send me, I'll just assume that you don't care. Okay, very simple. Okay, so what I want you all to do is look at the tutorial now. I'll tell you all what questions to do. Okay, I'll write it down also. Suck it out. It's going to be quite a bit because I will wish for a 4th lesson just to do tutorial questions. But I don't have time. Okay, really don't have. Okay, so homework. Again, you want to take 1 month to do, I really don't care. You just make sure you submit. Just tell me. Okay, level 1 and level up.
Level 1 again.
Okay, got 2 sets. We look at level 1 first. Question 3.
Oh, level.
Okay, level up questions. I know some are a little bit tougher. Okay, if I just at least want to see some effort, then I'll help you guys. Okay, what else?
Oh,
Okay, I'm just going to give you guys this. Go and do these patterns. Of course, guys, I say it out. Do it. You want to send me your iPad, soft copy, scan, whatever, just tell me. Just get it, just back. Again, I don't care how long you take to do this, make sure you do it. Just send it. If you don't send me, I'm just gonna assume whatever lah. That's even better lah. Okay, but don't rush it, guys. Okay, guys, don't rush it. Please look at the notes first if you're not sure. Don't feel confident, which is right now. Please look at the notes first. That's why I don't set it. This kind of thing. Okay, I know you are self-directed enough. Okay, go and try.